This is part 5 of the series Integration, and in this section we're going to get some practice in finding the upper and lower sum of a plane region bounded by the graph of a function. In this problem we have the function f of x equals x squared, and here we have the upper sum, and this upper sum is made by taking the height of the rectangles being the right endpoint, intersection with the curve. Here is the lower sum using the left endpoints, intersecting the curve. Let's first go ahead and find the upper sum, because it's going to be a little bit more straightforward than finding the lower sum. Now we're going to find the sum of the region bounded by the curve x squared, the x-axis, and the vertical lines x equals 0 and x equals 2. So let's now go ahead and write the form of our sum, and we have the sum for I equals 1 to n. That's the number of partitions or the number of intervals we're going to take. This picture shows 5, but we're just making a general case. We're just going to find n subintervals, and that's of f of x sub I, the height of each subinterval, times delta x sub I, the width of each subinterval. Now to find the width of each subinterval, what we need to do is take into consideration the boundaries, the upper and lower bounds of our region. So the delta x sub I, the width of each subinterval, is b minus a over n. The upper limit minus the lower limit over n, which is 2 minus 0 over n, which is 2 over n. So that's our delta x sub I. Now we have to find the height of each one of our subintervals. Since we're using the right endpoints, the height of the subinterval is going to be the function evaluated at the x-coordinate of that endpoint. And that endpoint is going to be made up of, this is x sub I, is going to be our lower limit, because we don't necessarily always have to start at 0. In this case we are, but we could be finding the sum of the region starting here over, or whatever our lower limit is. So it's the lower limit plus the index of our current subinterval. In this case, our current subinterval would be I. So we're taking the right endpoint, so it's the subinterval I, and that x-coordinate is going to be I, the number of subintervals, times the width of each subinterval. So here is the first subinterval, so it's 1 times the width of that subinterval, and we just found the width as 2 over n. So it's I times 2 over n. This one would be I plus 1 times 2 over n, and I plus 2, and so on and so forth. So this is the general term for our x sub I, the x-coordinate of our right endpoint of our subinterval. So now since our a is 0, this is simply going to be 2I over n. That's our x sub I. Now we can go ahead and substitute these values into our expression. So we have the sum for I equals 1 to n of f of x. So we're going to evaluate f. F is x squared. So it's the f of x sub I here, 2I over n squared, because it's that x value squared, times the width of the subinterval, this delta x sub I, 2 over n. And now it's just a case of simplification and then working out our sum. So let's go ahead and give ourselves some room here, and we're going to expand this squared term. So that's the sum of I equals 1 to n of 4I squared over n squared times 2 over n. Again, the sum of I equals 1 to n. This becomes 8I squared over n to the third. Now we can see here that we have two constant values. 8 over n to the third are constants. They're not going to be in the summation, so we can pull those two out. So what we'll have over here is 8 over n to the third times the sum of I equals 1 to n of I squared. Now we use our relationships with the sum of the counting indexes, and we have 8 over n to the third times n plus 1 times 2n plus 1 over 6. Now we'll continue our simplification, and 8 divided by 6 simplifies to 4/3. N divided by n to the third is 1 over n squared, and the result here is n plus 1 times 2n plus 1. Now we multiply this out. 4 over 3n squared times, that's 2n squared, that's n plus 2n, so that's plus 3n plus 1. Now we can combine these terms, and we have 2 times 4 is 8, and n squared divided by n squared is just 1, so that's 8/3 for our first term. Multiplying this by this, we have 4 times 3 divided by 3 is just 4, and n divided by n squared is 4 over n, plus 1 times this is 4 over 3n squared. Now this is our upper sum, and we can write it as big S of n equals that. Now if we were to substitute some number in for n, we would actually have a value for the approximation of the area of this subinterval using the upper sum. Now let's go ahead, and what we're going to do is compare this result with the lower sum. So let's go ahead and find the lower sum. So we've gone back to the top looking at the lower sum, and I've rewritten the form of our summation. And so what we're going to find, the sum is from I is 1 to n of f of x sub I delta x sub I. Now the delta x sub I, the width of each subinterval, hasn't changed. It's going to be the same as it was over here, and we calculated that as 2 over n. So we're going to use that same value. The trick is going to be finding this x sub I, the x-coordinate of our ith subregion. Now here is the first subinterval, and in this case we used the right endpoint, but in the lower sum we're using the left endpoint. So with this being the ith subinterval, we're actually looking for the I minus 1 endpoint. The ith subinterval, the I minus 1 endpoint. Ith subinterval, I minus 1. So the difference here in finding our x sub I is that we're actually going to have x sub I equals our lower limit, that didn't change, plus, instead of it just being I, it's going to be I minus 1 times the width of each subinterval. So it's not just the counting index, it's the counting index minus 1 because we're using this endpoint. So that's the distinction between lower sum and upper sum. Now we go ahead and work this out that becomes 0 plus 2I minus 2 over n, which is just 2I minus 2 over n. Now we can go ahead and substitute that back into our form, and we have the sum for I equals 1 to n of this quantity, 2I minus 2 over n. That's our x term going into our function, so that's squared, times the width of the subinterval, 2 over n. So now we've got some simplification to do here. So we have the sum of I equals 1 to n of, this is going to be 4I squared minus this times 2, 8I, and this squared, all over n squared times 2 over n. And we got to multiply this through, so we get 8I squared minus 16I plus 8 all over n to the third. So here we got lucky. We've got a common 8 inside here, so let's go ahead and factor some of that stuff out. We have 8 over n to the third times the sum of I equals 1 to n of I squared minus 2I plus 1. Now we could work these separate sums, or we can just work them in line. I'm not going to spend the time to separate these into separate sums, so let's just work them as they are. So that's 8 over n to the third, and the sum of I squared is n times n plus 1 times 2n plus 1 all over 6 times, or minus 2 times the sum of I, which is n, times n plus 1 over 2, plus the sum for I equals 1 to n of 1 is just n. And I almost missed it, but it's this whole thing times 8 over n to the third. Now I've gone ahead and worked out the rest of the algebra. If you'd like to follow through on that algebra, you can go ahead and pause the video and do that. But what I wanted to get to is I wanted to contrast the lower sum with the upper sum. So I've rewritten the lower sum here, and notice that the upper sum adds this middle term, the lower sum subtracts that middle term. If we use n equals 5 in this situation, the upper sum nets us an area of 3.52. The lower sum gives us a sum of 1.92. If you actually were to compute the exact value of the area under the curve, it's somewhere in between, which is 2.66 repeating. So you can see that the upper sum is a larger value than the actual, and the lower sum is a smaller value than the actual. But with 5 subintervals, we kind of get close, but we're a pretty good distance away. And we're going to look at what happens when we increase the number of subintervals and how that changes the accuracy of our estimate of the area under the curve. So let's go on to the next section and see how that works.